So, before we get started, a couple of things I want to announce to the room as a whole. We're going to be wrapping up chapter 1, and that means we're going to be doing specifically today projectile motion question and talking about how to look at the two-dimensional motion of projectiles. I've been getting via email some questions about the homework over the weekend, which is good. Please send me your questions as soon as you have them. And a lot of them have been about homework question number 5, which I would like to be able to talk about if we have time today, but I want to focus, at least from the beginning, on projectile motion, make sure we get through everything in chapter 1. I've also been getting questions about homework problem number 6. And number 6 is a projectile motion question. It's a lot like the one we're going to be doing here together today to introduce everyone to the concept. Since we're going to be covering new information that we used on your homework tonight, I have actually decided to move the homework and the quiz from tonight to Thursday. I'm going to be extending them so that you can take this information, use it tonight, use it tomorrow, and then come with questions on Thursday if you have them. Normally they'll be due around Tuesday, but if something like this happens again, I might push them to Thursday. So today will be projectile motion. That'll help you on 6. If you have questions about 5, because that's the second one I got the most questions about, we're going to get through projectile motion today, and I can try to set that number 5 up for you later today if we have any time for it. Additionally, again, please ask me questions at any time while you're doing your homework and during your quiz as well. Let's see. Other announcements. We do have lab this week. The setups that are taking up a little bit of the room are part of today's lab. I've been working to make sure that we are able to safely utilize the marble cannons as part of our experiment today. So now, we're probably not going to actually shoot them in here. I'm going to need to, between now and lab, I'm going to need to move them to the modified firing range I've constructed. But we do have a lab this week. If you are able to be here in person, we'll be utilizing the cannons and also doing some other activities. This will be sort of our first physical experiment. As it was connected to that, general lab policy is for closed-toe shoes. That is especially prevalent now because there's an increased risk that something might eventually fall on someone's feet. And I'm going to need you guys to call me on it if I ever show up in flip-flops, because I do that very frequently in summer. Sometimes I forget. So if I'm ever not wearing closed-toe shoes, please call me on it, because I want to make sure all of our toes are safe. Just utilize common sense. Don't drop anything on anyone's feet. We should all be fine. It's just safety precautions. So, homework quiz will be moved. Lab this week. If you're unable to come in person, let me know, and I'll work something out with you on a case-by-case basis. Any questions about anything before we continue?
I have a question on last week's lab, where it was like math movie.
Yes.
How did it that?
I have not finished grading them yet.
Because after doing a lot of old math stuff, it's pretty clear in the lab. You can go over that more.
Okay. Usually even though the lab is part of the class, I tend to talk about lab grades during lab, unless it's a big pressing issue that affects the entire class. I have everyone's assignment, and I have yet to finish grading all of them. The way that I do my grading is, at least historically, I would do everyone's first page so that I'm looking at the same question 1 for everybody and holding them all at the same standard. Then everyone's second page, and everyone's next page. I would expect, ideally, to have them done by next week. Usually I end up grading labs during lab when I'm not helping people. Please keep bugging me about lab grades because it's the thing that slips my mind to grade most often, which isn't good. Please nag me about it so that I remember. I would expect to get them by next week. So, and hold me to that, please. Keep reminding me. Yes.
Were we supposed to submit those to you by email if we did not come to the lab?
If you didn't come in person, email would be fine.
Okay.
Now, this week's lab, the canons are in person, but if you can't come in person, I can work something out with each one separately. Okay, any other questions? Decent Tuesday so far, I hope, all things considered. Okay, it's already week 3. I'm gonna fly through this pretty fast. When I was a student at this school, it felt like time moved slower in Clinton, but I think global pandemics make time feel like it's moving faster and slower at the same time. Time is a strange thing. It is relative, so there's evidence of that here. All right, I believe we left off discussing falling. We did work through this example, correct? The basketball player. Confirmation? We did do this one? Okay, here we go. So, did I throw markers and start talking about duty motion yet? Because I've had 2 other lectures since I last saw you guys. Okay. All right. Go ahead and go on here. So, we've done a couple examples that involve an object falling, and get my definitions back out. When an object is falling, which is to say, in a state of free fall, an object is being accelerated only by gravity. An object can be in free fall while it rises, because as soon as it leaves my hand, it is no longer being affected by any force besides gravity. So as soon as gravity is the only thing on it, it is in a state of free fall. An additional definition. Free fall is a state that an object can occupy, and if an object is in free fall, we define that object as a projectile. In order for something to be a projectile, it must be in a state of free fall, accelerated only by gravity. So, examples of projectiles would include anything that you throw, would include cannonballs, it would include arrows. It would not include rockets or planes that are actively flying, because those have propulsion systems, they have forces keeping them aloft that fight against gravity. Any object that is only accelerating in the air due to gravity is in free fall and is a projectile. Now, gravity on Earth always only acts in the vertical axis. And well, it's more accurate to say that gravity is always going to point towards the center of the Earth. But since, as far as all of our human eyes can tell, the ground is pretty flat wherever you're standing on Earth's surface, it's always just going to point straight down. But gravity can only act vertically. It cannot cause something to accelerate horizontally. So we're going to begin looking at the motion of specific projectiles as they are falling and moving sideways at the same time. Falling and moving sideways at the same time. So, yeah, please remind me if I did this last time. This marker is just going to drop straight down, and I'm going to flick this one straight out. which one would hit the ground first?
One going straight down.
Okay, why would one assume that? It's a reasonable assumption to make, but why would that make sense on some level?
Straight, right. The path going down is longer than the path going straight down.
Okay, it is the shortest distance between any 2 points is a straight line, and if the one that I drop is only going straight down, you're right, it is going to travel the least amount of distance. But watch if I actually do it. And some of you are just going to have to listen for the thumb, because I know this spot of the floor is not very easy to see. What happened? They hit at the same time. I'll do it again on the other side of the room so that it'll get on camera. So the black one is going to fall straight down. I'm going to flick the green one only sideways. So which one hit the ground first?
You can at the same time.
Same time. You are right. The black one that falls straight down is traveling the least distance, straight line between where I drop it and the floor. But they're still both covering the same vertical distance, and they're still accelerating downwards at the same rate. The only difference between the two is this one is moving forwards at the same time. It's moving in two axes separately at the same time. This is two-dimensional motion. We've been looking at only one dimension at a time. Now we're going to look at both of them together. And the secret to looking at both of them together, the secret to two-dimensional motion, is actually that each axis is still completely separate from one another. What happens in the vertical axis does not directly affect what happens in the horizontal axis. Both of these objects, if I drop them from the same height, and I don't throw them straight down, will take the same amount of time to fall, regardless of if I project one of them sideways. Because no amount of sideways motion will ever affect how fast something moves down, except in the case of a plane designed to do so. But that's the exception. So, the two axes, when we're looking at two-dimensional motion, and that is what is pictured on the board here, an object moving in 2 dimensions. So the red ball is being dropped straight down, the yellow ball is being thrown sideways as it falls straight down. This is two-dimensional motion. We're moving in the x and the y at the same time. Notice at every time interval, even though the yellow ball is moving sideways at a constant rate, their heights at each time bar are the same. The horizontal movement had no effect on the rate at which it fell. I'm going to put a slightly different picture on screen now. This, rather than being dropped, is an object that is thrown kind of football-like. So it is thrown forwards and up at the same time. What we're doing here is we're going to analyze the movement within each axis as we go. So, if you chuck a football, usually you're going to throw at an angle because you want it to go up and forwards. So, its starting velocity, this arrow here represents our velocity vector. All vectors can be drawn with an arrow. This vector here represents our initial velocity. It has both a vertical component, the ball is going to go upwards, but it also has a horizontal component. It will go horizontally at the same time. Now, gravity only works in the vertical axis. So notice the vertical component keeps shrinking. This is the same case as the basketball player. When you throw something upwards, even though it moves up, it's accelerating down the entire time. as long as it's in free fall. So its upward velocity becomes increasingly negative the entire time. But gravity only works vertically. The horizontal piece remains constant. It's tiny, but it's the same size the entire time. So even though the vertical velocity is changing because of gravity, the horizontal velocity remains the same because there's nothing causing it to accelerate in the horizontal axis. I'm going to put a sample question on the board real quick, just to sort of point at it and use it as an example that we will do later in the lecture. I'm just going to put it up on the board so that we can go ahead and I can show you the picture that I drew over there of it. Let's say that you're standing on the top of a cliff and you throw this ball horizontally sideways at 21 meters per second, which is a very fast pitching arm. Congratulations. So, we're told 9 meters off cliff, and that the ball is initially projected outwards horizontally at 21 meters per second. If I throw it, 21 meters per second. If I only throw it sideways, what is its initial vertical velocity? 0. If I throw it sideways, and only sideways, initially isn't moving vertically. So, we would list, if we're listing our variables for this particular question, our ball starts at the top of a 9 meter tall cliff, but if this is sort of an XY plane, this point up here would be 9 up in the y-axis, but 0 in the x-axis. We haven't moved from the origin in the x-axis yet. So that's why I have listed up here 9 meters displacement in y and 0 meters displacement in x for the initial beginning of the experiment. For velocity, the 21 meters per second is only in the x-axis. Meanwhile, on the y-axis, if you only throw it initially sideways, its initial y speed is 0. When you throw something only sideways, its initial y is 0. It's not really falling down until it leaves your hand and gravity begins slowly pulling it down. Next, the acceleration in the vertical and the horizontal axis. The vertical acceleration of this ball is going to be due to gravity. Gravity is going to start pulling it down the entire time. So the vertical acceleration is going to be negative 9.8 meters per second squared. But this object is in a state of free fall. The only force acting on it is gravity, is a projectile. If gravity is the only thing causing this ball to accelerate, and gravity only points down, that means that there is no x acceleration. None. So what does that tell you about what's going to happen to this horizontal speed throughout the entire process? Sorry, horizontal velocity. It's going to stay the same the entire time. Horizontally speaking, the acceleration is 0. And I realize that I've drawn a very bad x. This is supposed to be an x, but it didn't make the extra leg look very different from my y's. That's a x. My x acceleration is 0. The acceleration is the change in velocity. So if the x acceleration is 0, the x velocity won't change. If there's no force, if it was to create an acceleration in a specific axis, the object won't accelerate in that axis, and it will just keep doing the same thing forever. I'm going to switch slides for a quick second to go ahead and show you something that we'll talk more about in chapter 2. What I'm about to put up are Newton's laws of motion. Only look at the first one right now. These are Newton's 3 laws of motion. They're very important. You've interacted with all of them before your whole lives. Right now, just pay attention to the wording of the first one. So Newton's first law of motion says, an object at rest stays at rest, or an object in constant motion stays in constant motion unless acted upon by an outside force. On the one hand, what this is saying is, if I put this marker here, and nothing ever touches it ever again, if all of its forces remain the same, if all of its accelerations remain the same, it's just going to stay there forever until something comes in and does something to it. But what this law also says is, an object that is moving at constant velocity will keep moving at constant velocity indefinitely until something stops it. Which is why that ball thrown horizontally off the cliff, since there's no acceleration in the x-axis, it'll just keep moving at the same velocity forever until something stops it. Now, when you throw a ball off a cliff, what's going to be the thing that stops it? Hitting the ground. Eventually, you're going to hit the ground. You won't be able to move any further down. You won't be in the air to be able to move sideways anymore. So eventually, it's going to hit something, it's going to stop. But until it hits something, it'll keep moving horizontally at the same speed indefinitely. Have you ever seen in space movies where some object, a meteor, a piece of shrapnel from the ship, it's thrown away from where the actual movie is happening and it just keeps drifting forever? That's because in space, there's nothing to slow you down. There's no gravity, there's less gravity, and you're not likely to hit anything to make you stop. That's kind of the ultimate case of an object in motion will remain in motion until something stops it. It'll keep drifting until it hits something or it gets caught in a gravity well. So this is a tiny downscaled version of that. So, introduction to Newton's laws. We're only looking at the first one for right now. Is everyone okay with this definition so far? Okay. This slide will be available in the chapter 2 notes. I'm just putting it up now sort of as a preview and an explanation of the constant s speed on the cliff. So, examining the cliff question specifically. We've looked at each of our axes separately from one another. And the trick to looking at two axes at the same time, to do motion, is you still have to keep both axes separate. What happens in one does not have any immediate bearing on what happens in another one. Which is why I've listed basically each variable twice, once for the x-axis and once for the y-axis. Like when I threw them a second ago, how fast you move horizontally does not affect the speed at which you will fall straight down, which is why we do have to list our formulas out twice, basically. When you're working these types of questions, you're going to kind of want to just, most of the time, you're going to use each formula twice. Once to look at the x components, once to look at the y components. You can't mix the two under normal circumstances. If the variable has a y next to it, it can only be plugged into the y version. Okay? so far? Okay. There's one exception to that. If you look at the way that I wrote these, what's the one variable between both versions of this formula that's the same, completely the same? T, time. Why is time not specifically being divided into x and y?
It's not on axis or anything.
Right. Time has no direction. It is a scalar, not a vector. Scalars, you don't have to bother differentiating because the amount of time that you fall down is the same amount of time you have to move sideways. If it takes you 5 seconds to fall down, you only have 5 seconds to move horizontally before you hit the ground. So time is going to be the same across both because it's the same time. It's a scalar, it doesn't care about the direction of anything. Cool? Okay. So, we're going to utilize these formulas in a minute. I've been talking for a decent amount of time and I'm thirsty and need to take a deep breath. So now would be a good time if you need some water or go to the restroom, go ahead. I'm going to take a minute to make sure there's oxygen in my lungs. Okay. Any questions, concerns, thoughts, or haikus? Okay. So, just talked about, we're actually going to, that's the wrong slideshow. We're actually going to solve the question, find the variables that we were asked for in this question. This will be very similar to the specifically homework question number 6. Very similar to what we're going to be doing with the cannons this week in lab. So do take notes, because this type of question is a projectile motion question, because it's about the motion of a projectile, and they all work very similarly. You may end up doing it sort of in reverse from how we do it, but how we do it here today is going to be very similar to most of the projectile motion questions. They might all look a little bit different. For example, homework question number 5 involves an old-timey musket, I believe, and that ball that it fires is just going to be the projectile instead of the ball being thrown here. But they all work on the same mechanics. They're all going to be very similar types of problems. Cool? Okay, so you stand at the top of a 9 meters tall cliff and you throw a ball horizontally this way at 21 meters per second. We're standing 9 meters above the ground, so our initial Y height is 9. We're considering our starting point in the x-axis to be 0. If we, again, look at this like a coordinate system, this origin right here would be 0, 0. This point would be 0, 9. We are 9 meters above our starting point of 0. Again, our starting velocity in the x-axis is 21. Our y starting velocity is 0. Y acceleration is gravity. X acceleration is 0. So, the first thing we're asked is, how much time will pass before the ball hits the ground? Excuse me. So, time before it hits the ground. We want time. We know in both axes, displacement, velocity, and acceleration. So, first of all, what formula do you think we should use to try to find time in this case?
Could you not use that formula?
You absolutely could. Honestly, Formula 3 is going to be the one you probably use most often. My next question is, though, which axis should we look at, X or Y, to help us best figure out time spent in the air? Okay, so the x-axis is interesting because okay, I'm going to do the marker thing again. I'm going to throw this one sideways, I'm going to drop this one straight down. Any difference there was just due to my lack of coordination when it comes to throwing. Did the X movement change when it hit the ground? The black one was thrown sideways. Did that affect when it hit the ground versus the one that was just dropped? No. What would affect how long it took one of them to fall versus the other? Height from the ground. If I wanted the marker to be in the air longer, I could drop it from higher up. I could also just throw it upwards and just drop the other one. But both of those are in the vertical axis. So on Earth, where gravity works up and down, the vertical axis is always going to be what affects your hang time. Hang time is essentially what we're solving for here. It is the time in the air of a projectile. It is the amount of time you have before you hit the ground, which is also the time you have to try to move out and cover however much range you have to your target. So, put it in the corner of your notes. Useful tip to know, the vertical axis always determines the time spent in the air. Vertical axis will always determine time in the air. as such, let's look at the vertical axis first to figure out time in the air. Where is eraser? There it is. So, we first asked for time in the air. So let's look at the vertical stuff first to figure out and solve for time. So, first thing here is delta dy. What is going to be our total change in displacement in the y-axis during this process? We know we start up here, 9 meters above the ground. Where's the ball going to end? It's going to end at the ground. The ground is 9 meters below this point. If we consider this level to be 0 on the y-axis, then the rule with delta anything is always a final minus initial. I'll rewrite that real quick. So dy final minus dy initial. Delta anything is final minus initial. So our final y location is going to be the ground at height of 0. So that's what we're going to plug in here. Our initial y location is 9 meters above that at 9. So our displacement from this, our vertical displacement for this entire process is 9 meters down. We've descended 9 meters. The ball will descend 9 meters. And because we went down, and we defined down as negative, that's why we're going to get a negative number here. Later on, it's going to cancel out with a negative on our gravity, and we will get a positive number for time like you would expect. Next, we got our delta displacement right here. This is just going to simplify to -9. Now, our initial y velocity is 0. Doesn't matter how long you spend in the air, your initial is still 0, so this whole term is just going to fall away. And then 1/2 times ay times t squared. So 1/2 times -9.8 times t squared. And t is the only remaining variable, so we can use this to completely solve for time and get the answer we want. Now, go ahead and while everyone's copying this down, me looking at this, I know that we could do a quadratic on it if we wanted to. We've got a constant term with no t, a term with just t, a term with t squared. We could do a quadratic. Why do we not have to? What can we do to simplify this very quickly?
You need to get t by itself. You can get t squared equals something, and you can just take the square root of it.
Yes. Ultimately, this term is just going to fall out. It's the 0. We just get rid of it. So if I simplify this one line down, -9 equals, this would be 1/2 of -9.8 is -4.9 times t squared. Now we don't need a quadratic, we can just find t, the old-fashioned way. So if you have your calculators as well, get those out, make sure you can get the correct answer with me. Let me know what kind of time we're looking at. Anyone disagree? All right. Court finds in favor of 1.36. I'm just going to round that up. What would our units be? Very good. We were solving for time, and we put in meters per second squared, so that simplifies down to seconds. Court finds in favor of this answer. Motion carried. So the ball would be in the air for 1.36 seconds, which again might not seem like a lot, but if anything is falling for that amount of time, that's a long time to be falling. Now, this same method, notice, as long as you are falling straight down on planet Earth, and that would make this number the same every time, and if you are dropping the object, if its initial velocity is 0, then the only thing that's going to differentiate what we did here from, say, any other cliff or building you drop something off of is the starting height. You can plug any starting height you want into this, and that will tell you time in the air. Because as long as you're on Earth, where this is true, as long as you are just dropping from a starting y velocity of 0, this is how you find the time it will fall. And that will be true, ignoring air resistance, which we will always be doing because air resistance is a huge pain. Ignoring air resistance, all objects dropped from 9 meters will take 1.36 seconds to hit the ground. Cool? Okay. Keep this in your back pocket because this is what you'll be doing for almost anything that is falling some amount of time. But we figured out time in the air. Very good. A word used to describe that term would be hang time. It is the time you are hanging in the air. Now, we have time, and as we previously discussed, time doesn't really care about what axis you plug it into. Time is a scalar, and it's not bothered if you're looking at x or y because it's going to be the same across both. So now that we have this time, we can plug it back into the horizontal equation as well. So, the next part of the question asks, how far from the base of the cliff will the ball hit the ground? What we're being asked for here is the range. The range is the horizontal displacement of a projectile. So, historically speaking, cannon operators would have to do these sort of calculations. They'd have to calculate the range of their weapon in order to figure out where they're going to hit, figure out where they need to place the cannon, what angle they need to have it at in order to actually hit their target. So what we're doing here, range calculations, has gone back a very long time to people who are desperately trying to hit their target. So, this projectile motion is a range calculation, and now we're just going to figure out how far from the cliff, the horizontal distance that we're going to travel to figure out, where we're going to land. And the change in horizontal displacement is this, delta dx. From start to finish, we want to know how far we traveled horizontally. So this already is what we want to solve for. So let's just plug in everything else now. So this is the horizontal operation that we're going to be doing. This is still Formula 3, but we're only looking at horizontal components. Horizontally, we want to know delta dx, so we're going to leave that alone. Our initial x velocity is 21 meters per second. And then we multiply that by time. We already found time just a moment ago. So we can plug that in for t. Then we have 1/2 times x acceleration, which is going to be what?
0.
0. There is no x acceleration as long as you are a projectile in free fall. So it doesn't matter anything else. This entire piece here is just going to go away because of that 0. Which just leaves us with delta dx equals 21 times 1.36. Very good. What would our units be? Meters. We solved for distance, so that is going to be in meters. This is the physical distance that we land from the base of the cliff. And that's about 100 feet, so whoever this is a good throwing arm. And that is your basic range calculation. Most similar projectile motion problems are going to work exactly the same way. Although, sometimes, depending on the question, you might be asked to work in reverse. When we do physics examples in this class, it's going to be impossible for me to show you every single way we could use a formula, every single type of question, because all these formulas are incredibly malleable. We use them to describe everything. And any possible way that a formula can be, like, algebraically, you can rearrange those formulas in tons of different ways. So there's going to be lots of different types of sample questions. There's going to be lots of different types of homework and quiz questions. And there's no way I could possibly cover every single scenario with you guys. What I am going to try to do is cover a lot of different base scenarios and show you, how we can use algebra to rearrange our formulas, what types of things they can be used for. But occasionally there's going to be, like I said, if you've been looking over the homework, question number 5 is about a musket firing an old ball, and that type of question is going to work exactly the same way, even though mechanically it doesn't quite resemble throwing a ball off a cliff. But it's going to have sort of a very same way that you do it. Subsequently, there might be a question where you are told the range, and you're asked to work backwards to figure out the time in the air. In which case, you sort of just work in reverse. You know the range, you can find time in the air. Range, you can find time in the air, and then you figure out how far it fell. So there's going to be lots of different permutations. Excuse me. There will be lots of different types of permutations of the things that we have done. But the methods, the formulas, the algebra is all going to be useful and carry through. And if there's any questions about a specific example, because it's just different to how you would have pictured it going, let me know immediately and I will work with you guys. Speaking of specific questions, we have some time to talk about specifically homework number 5, because I've had a lot of people ask about it. So I can give you guys sort of a primer on that one. I have already, just now while we were taking a breather a second ago, moved the homework to be due on Thursday. So you can take what we did here, use it tonight and tomorrow, come to class with questions, and get them answered, and then continue on, finish the assignment by Thursday. By the end of today, and definitely Thursday, we will begin moving on to Chapter 2, which is just the direct continuation. We've already introduced most of the concepts. It's just, the next little piece. And since we're beginning Chapter 2, I will soon be posting the chapter 2 homework and quiz, but those will probably due Tuesday after next. Okay? That's just the starting due date, depending on how fast we get out of it. Depending on how long it takes to get through the chapter. So, before I put homework 5 up on the board, just to give everyone a primer on it, does anyone have any questions about anything at all? Okay. I'll put 5 up in a second. I need water, stay hydrated, everyone. Now, if any of you have been working with each other on homework questions, if any of you have been working with each other on homework questions, you might have noticed everyone's homework questions might look slightly different. The question will all be the same, but everyone would have different numbers. And what Sapling does is it has the framework and the programming for how the question works, and it generates a set of numbers per student so that no one's examples are exactly the same. I do encourage you all to work together, because if you can help each other figure out how to do it, then you take that knowledge and use it on your own numbers, which I feel is better for learning it, because you have to understand the formula and what the algebra means, and then plug your own numbers in. I encourage, want all of you guys to work together on that. Please do. But, just to make everyone aware, if you haven't noticed yet, every student does have their own slightly different numbers. So, what I'm about to put up on the board now won't look like your numbers, but it is the same question. We will work it the same way. So, we got homework question number 5. And does everyone have these copied down? Okay, if I make some space. All right. So, first thing we do, we always read the question, then we list what we know and don't know. But another good first step is drawing a picture, which I'm going to do for you guys now. Feel free to copy it down because, again, it's the same physical setup. You can use this picture for yourself. A ball is dropped from an upper floor some distance above Tom's apartment. So this is taking place in an apartment complex. Let's say this window right here is Tom's window. Okay, now we know a ball is dropped somewhere from up here, and as most falling objects do, it's going to fall down, and it's going to zip past Tom's window. So, he looks out of his window, and this particular window has a vertical axis measurement on my screen. Your numbers might be slightly different, of 1.5 meters. Ultimately, this distance is a known factor on all of your problems. Whatever your number is, you do know what this is. It's a variable that you can use. And Tom, so hang on. Let me list displacement window. Known, and the time it takes the ball to zip past this window is known. And what we are asked is how high above the window is the ball originally dropped. So we want to know height above the window that the ball fell. We don't care about the height of the building. We don't care about where the window is in the building. We just want to know how high above this window was the ball dropped. Now, because it is falling, there's another piece of information we can automatically assume, and what do we assume about all falling objects?
With acceleration of 9.8.
Yep, acceleration is going to be negative 9.8 meters per second squared. Now, as we're working this problem, there's going to sort of be two different phases. And in both phases, this is always true. It doesn't matter what part of this journey you're looking at. If you're looking at ball falling to the window versus ball falling past the window, in both stages, this is true. This is the constant across both. Now, I'm going to try to go ahead and start pointing you in the right direction. I did say that there are two phases here. And you kind of need to work backwards from Tom's window up. Phase one, you're going to use this formula to look at the ball as it passes Tom's window. As it passes the window, you know the distance it travels from here to here, and you know how long it took, and you know its acceleration during that process. So we know D, T, and A. Those pieces of information only exist together in Formula 3. The remaining variable in Formula 3 is initial velocity. But if we're looking at just the window, that's going to be the initial velocity as it's beginning to crest the window. So if you solve for the initial using this information about just the window, this will be velocity as ball reaches top of window. But you know the length of the window, you know the time it took to cover the window, you know acceleration. You can safely find the velocity when you reach the top of the window. So that is what this part, that's the information you can gather from the first phase of the question. Once you have that piece of information, you can move on to phase 2. So I'm just going to throw a sample number out there. Say we plug everything in, we solve for VI, and VI that we get here is like 20 meters per second. Just to have a sample number real quick. If we found 20 meters per second here, that means at this moment, when we begin the stopwatch and we see that it travels this distance, this amount of time as it passes the window, right here it was moving at 20, or whatever your numbers would tell you. This point would be the initial, looking at the top of the window to the bottom of the window. But this point would be the final if we look at the ball's initial height down to the top of the window. This number, whatever you find here, can be used as the final velocity over this height. It accelerated from the top to the window up to this velocity. So for that phase, for the phase from top to window, this is V final. Which means, one other piece of information we can actually pull out of the question is, the ball is dropped. So what does that tell you about its very initial speed up here? 0. So we know its initial velocity up here, its final velocity here. We know its acceleration as it goes between these 2 points. What we want to know is the distance between those 2 points. So what formula does that sound like? Final velocity, initial velocity, acceleration, displacement. Formula 4. Formula 4, velocity final squared equals velocity initial squared plus 2AD. We know it was dropped, so at the very top of the building, this is our initial velocity, plus 2 times our acceleration, which is still negative 9.8. That's the same, it's the same gravity, the same planet for the whole thing, times D. We want to know the displacement from here to here, so we're going to end up solving for D. And this is the velocity final after it has covered, after it has fallen that distance. We know that after falling this distance, it would be moving at the speed we just found in phase 1. So whatever number you get for VI, what you then plug in there. It's the initial speed for the window, but it's the final speed going from top down to the window. Cool? Okay, we got at least one person saying not cool. Any specific questions? What can I do to help you with this? Okay. Again, I've moved the homework to Thursday. So between problems 5 and problems 6, take this information, give it a shot, let me know how it goes. You can email me your immediate questions. You can all bring your questions together to lecture. And again, that said, the sooner you ask them, the better, because if I know everyone's still having trouble, I can come prepared to lecture to help. So send me emails. Cover it again on Thursday as a group if we need to. And let me know how it goes. I'm going to help you guys figure it out. Now, we are reaching the end. If you do have Tuesday lab, I'm going to be sort of last minute reconfiguring the Canon setup before lab actually starts. If you want to question or do anything, you can. I'm going to go ahead and introduce chapter 2. Not going too fast yet, but just to show you what we're going to be doing next time in the last couple of minutes here. This is literally just the next step. We're taking what we've been talking about, applying just a little more to it. So, chapter 1 has been about the basics of motion. Chapter 2 is going to be what creates motion in the first place. So, we're going to be talking about Newton's laws and how they affect our motion and our basic understanding of mechanics. The word mechanics gets used to refer to physical systems. Comes from the Greek word mechanos, anything involving physical objects moving or sometimes not moving. count as mechanics. So we're going to be looking at Newton's laws and how they affect whether or not things move or whether or not things are not moving. Now, Newton is very important. For hundreds of years, Newton's laws were like the golden standard for how we understood the universe. Eventually, we found that they weren't perfect. I think I mentioned the specific example of we could not use Newton's laws to track the orbit of Mercury, and so we had to, Einstein came along and proposed general relativity, which allowed us to better track Mercury's orbit. But up until Einstein, until Einstein, Newton ruled for centuries. And Newton's laws are still incredibly important, which is why we're still talking about them, it's why we're still teaching them. You've been observing them your whole life. You've been told them before. You know them. You've heard the words. You've seen the formula. And these are the three that we are going to spend the next week or so talking about. We talked about the first one today. Object at rest will stay at rest. An object in motion remains in motion. Like I said, something drifting through space will keep moving at constant velocity because there's no forces acting on it. It just keep moving forever. The second law is a formula. This is probably the one we're going to spend the most time working with because this formula is going to come up forever, now until the end of the class almost. And what this says is, remember what this symbol means? When this shows up in math, what do we use it for? The letter? Sum. S-U-M, sum of. So, sum of all of the forces on an object is equal to that object's mass times its acceleration. The layman's version of that is the harder you hit something, the faster it moves. Also, the heavier something is, the more force you need to act on it to make it go. I did Taekwondo when I was a kid, from like age 10 till the end of high school. And the way my instructor always taught us this when we were doing breaking boards is, if you want to hit something harder, if you want to punch something with more force, you need to either be moving faster or you need a bigger fist. So that got drilled into my head at a pretty early age. Last one, just real quick, for every action force, there's an equal and opposite reaction force. When you punch that board, the board is going to punch back. Do not injure yourselves. And for the record, we didn't do a lot of board punches. It was mostly kicks and palm and elbows. So, this is going to be the next week or two. Very foundational to the rest of the class. We're going to keep going over them. And this new slideshow will be available today for you to go ahead and start perusing. Wrap up your chapter 1 homework though. Send me your questions as soon as you have them. And have a wonderful day.
Do we need to go back and get those sheets?
It would be wise. That said, your options are, I will let you do this one with a lab partner if you're asking me to work with you, like, very closely, physically, or I can just give you the digital assignment. But the digital assignment involves simulated, I don't know if it's just a long. You have to do that? Okay. Let me turn the camera off and see what everyone else has to say, and I'll get back to you, sorry. Thank you very much.
It's not stapled, so I like fold it to.
Yeah, that's what I've been doing, because there's no staplers on this floor for some
Yeah.
reason. I need to find more.
Yeah.
I have one question about the homework.
Yes.
With the entering answers into it, is there a limit to the amount, or like how far is it